All right, so 2 more sections to do here in Unit 2. This one's focused on uniform circular motion and the effect of it on various surfaces. So I don't know why those are going first, but those are different things. So an object that moves in a circle, I forgot the word in. So in a circle at constant speed, it's experienced uniform circular motion, or UCM, where the magnitude of velocity will remain the same, but the direction is going to be continuously changing. With the direction of velocity changing, there's obviously an acceleration, and we call that centripetal acceleration, which means if there is a centripetal acceleration, there is a force. And how do we calculate that? Well, it's going to be A sub C equals V squared over R. And then the force then becomes MAC, or MV squared over R. But sometimes the V is given to you in a weird way. It may tell you that it takes an object to go, it does essentially the circumference of a circle in this amount of time. So your V would be 2 pi over T. But this is also what we call translational speeds, right? And so this is the what amounts to the perpendicular speed to the circle. So one thing to note, that the centripetal force is not a force that is drawn in a free body diagram. It is the net force that is causing the acceleration. So again, centripetal force causes acceleration. It is not a specific force. Okay. Now, many UCM problems will take the form of Newton's second law problem. So instead of writing your equations as horizontal and vertical, you'll want to write them as circular and non-circular. And there can be problems where the object's velocity is not constant, which means that the acceleration and the force will have components to them. And especially with the acceleration, we'll say that there is a translational acceleration, or a perpendicular acceleration, and the centripetal acceleration. So if the velocity is not constant, like if it's changing over time, that means that we have various accelerations happening. Very common questions that you see here, the ball, right? So your velocities will always be perpendicular to these situations. So you have the Ferris wheel, and they'll talk about like what is the normal force at the bottom, and maybe a car in a car in a valley, a car going over a hill. The string, right? It'll talk about the tension. So one thing to note here, right? In this case, the normal force is inside the circle. In this case, the normal force is outside the circle. And another thing is to make sure that the acceleration, centripetal means center seeking, so it's always going to go towards the inside. And then with the ball and the string, the tension is going to go inside. And you can see it's a little bit different. Like the tension's a little bit less at the top than it is at the bottom. The conical pendulum, where the tension is up in the inside, and you have to break down, but it's going in a horizontal circle. Okay. And so you look at your free body diagrams and you create, everything off of that. And then finally, going around a turn. So every turn has a radius, and you can figure out how fast you have to move to go in that radius. Okay. And in fact, the example for here, we're going to look at a banked turn, which is a very common question that pops up. And so here I have a car traveling on a surface, right? A banked turn. So what happens is your centripetal force is going to be inside, because I'm looking over the top. It's making the turn here, right? So my centripetal force and acceleration is going to be to the inside. I'm going to have a normal force, and then I'm going to have the weight down, right? So typically when we did inclined planes, these would be, X and Y directions. But what we're going to say, what forces are causing circular motion and what forces are helping with the circular motion and which ones are not. So normally what we would do is we would break apart the velocity, or excuse me, the weight into components. But because circular motion is horizontal, we're going to break apart the normal force. okay, into x and y components. So it's going to be fny, fnx, okay? And so what we're trying to find out in these problems is what speed, okay, or the formula for at which angle should it be banked so no friction or is required, and then what is the angle for a road that has a curve, a radius 50 meters, and with a design to be 50 kilometers per hour. So again, I'm going to create my T chart, but I'm not going to call them X and Y. I'm going to call them circular and non-circular. So I've got centripetal, right, is equal to MAC, right? That's my net force. And so the only force that is acting is FNX, okay? And so that's going to be equal to MAC. But my problem is I don't know what FN is, so I need to go over to my Y direction. And so I'm going to have the sum of the forces in the non-circular direction is going to be FNY minus FG. Now, FG will be our one. So here we're going to create like circular, non-circular, right? And so the only one that is now going to be in the broken apart will be our normal force. And so that's going to tell me, and I'm not accelerating in that direction, so it's going to be equal to 0. And so I have FNY equals FG, but FNY is going to be FN cosine theta. Okay, and so that makes FN equal to FG over cosine theta, or MG over cosine theta. Okay, so now I can go back over to my equation, my circular side, and say, okay, Fn is going to be Fn sine theta is equal to MAC, but I'm going to take this now, or this right here, plug it into there. So it's going to be mg sine theta over cosine theta is going to be equal to MAC, and that m cancels that m. Sine over cosine is tangent, so I get g tan theta is equal to AC. Okay, now we're going to write this in terms of VGR. That's often what happens when they do on the AP test, is they're going to tell you what variables to write this in. So I'm going to substitute V squared over R equals G tan theta. All right, I'm going to divide by tan theta, or excuse me, not tan theta, but G. And now all I have to do is say the arctan or inverse tangent of V squared over GR will give me my angle. Okay, so that's my answer to part A. Answer to part B is now we're just going to plug in our values. Let's say inverse tangent of V squared, so we have to convert 50 kilometers per hour to meters per second. So again, 1 kilometer is 1,000 meters, and then we have, this should be seconds, sorry. 1 hour is 3,600 seconds. So I'm going to say 50 times 1,000 divided by 3,600. And so it's going to be about 13.9 meters per second. So I'm going to do 13.9 squared over 9.8 times 50. Make sure your calculator, again, is in degrees. So I'm going to say inverse tangent. Oh, I have it worked out. That's going to be 21.5 degrees, right? So 21.5 degree banking, so friction wouldn't be involved at all. Okay, so that is kind of the more advanced centripetal acceleration equation. But there are things that happen that if you go through, and maybe I'll do another video basically talking about what happens when objects slide and so forth. What does like some of those equations look like? But we're down to now just what amounts to the calculus of this particular area this particular unit, and the velocity